I'm Erica Zavaleta, and this is Ecosystems of California. California's subalpine ecosystems are the highest elevation systems that are still dominated by trees. Subalpine forests are defined at their upper limit by tree line, and they exist in an environment of short growing seasons, extremes of wind, desiccation, cold and drought, and poorly developed soils. Their lower limit is defined variably. Where they meet montane forests depends on things like the history of fire in a region and the opportunities for subalpine species to expand down into gaps created in the montane forest by disturbances like fire. Moisture arrives to these systems almost entirely in the form of snow, which is a challenge because that snow becomes available very briefly as water before the dry summer arrives. For a visit to subalpine forests, we've decided to focus on the ancient bristlecone pine forests of the White Mountains in far eastern California. There are many different kinds of subalpine forests in the state, defined by variation of climate and soils, but the bristlecone pine forests here exist on these ancient dolomite soils. I'm in a dolomite fell field here, an environment marked by a lot of rock as well as these poorly developed soils. These dolomite substrates, the rock itself, are Precambrian in origin. They're 600 million years old. They're part of an ancient seafloor. They were laid down as sediment, calcium carbonate originally, in the shells of ancient animals. And over many, many years, these sedimentary ocean floor bottoms were lifted up by larger tectonic forces that created both the Sierras, which are dominated by granite to our west, and the White Mountains, which are dominated by these sedimentary rocks. Dolomite is nutrient poor. It's unusual in chemical composition, and so there are not very many things that can grow here. The understory is unusually sparse, even for a subalpine forest. There aren't very many plants growing besides the bristlecone pines, and those that are mostly herbaceous plants and not woody species. The ancient bristlecone pines themselves have a number of adaptations to deal with these extreme settings. They can hold on to individual needles for up to 50 years, which is much, much longer than your typical conifer, and their needles have this very waxy resinous coating to protect them. That's because a long period can go by in which there aren't water or nutrients available for the tree to invest in making new needles. They grow really, really slowly. They grow most slowly on a slope like the one I'm standing on. These trees are growing slowly and putting down really, really dense resinous wood as a result. And so it turns out that the very oldest trees are the ones in the harshest environments, like this hill slope. This tree behind me looks dead for the most part, but a small portion of it is being supported by a thin strip of cambium that is carrying water and sugars up and down in the living bark, the cambium, and supporting just a small portion of the canopy of the tree. So most of it has died back, and that small portion of living canopy doesn't require as much water or nutrients to persist. So trees on this slope are on the order of 3,000 to 4,000 years old, potentially. And another adaptation to these extremely harsh environments that bristlecone pines exhibit is that they can remain reproductive for thousands of years. So over much of that long lifespan, they can still produce cones. And that's important because replacement in an environment like this can happen really, really infrequently. So the ability to try to reproduce over many thousands of years gives individuals the opportunity to hit what might be a once-in-a-century opportunity to reproduce successfully and produce seedlings. Bristlecone pines are famous for their longevity. They're the oldest known non-clonal living organisms on Earth. And in 2012, an individual in this area in the White Mountains was dated at 5,062 years old. An individual even older than that, 5,200 years old, was described earlier in the 20th century elsewhere in the Great Basin. Because they grow slowly, their growth rings are really, really small. But because they grow in this really extreme environment, in this high elevation, arid setting on really nutrient-poor dolomite soils, their growth is sensitive to changes and variation in climate and other conditions. And so because of that, study of their tree rings, dendrochronology, has been a valuable way to reconstruct climates throughout the Great Basin region over the past 11,500 years, so dating back all the way into the Pleistocene. And the way that scientists have gone back beyond the ages of the oldest living trees and into the 6,000 odd years before that is by cross-dating rings in living trees with rings in long dead trees that haven't decomposed because it is so high and dry here. And so they're able to line up rings in living individuals with rings from wood on the forest floor and to reconstruct through those overlapping sections a continuous record of 11,500 years. The other thing that bristlecone pines have allowed and that have really revolutionized our understanding of history is that in the past, people dated major events in ancient history using radiocarbon methods directly on artifacts. So for instance, a piece of a pottery shard from Mesopotamia would be dated using radiocarbon methods. But scientists weren't able to take into account how variations in the Earth's atmosphere over thousands of years affected those radiocarbon dates. And so when I was a kid in school, the dates that we were taught were all underestimates of how long ago various things happened. So it turns out that when you radiocarbon date tree rings in that 11,500-year-old record, so that you know exactly how old you're looking at, so you can recalibrate the carbon-14 dating scale, that shifted dates of many events ranging from the advent of metal tools in Europe to the time of the pyramids and the rise of civilization in the Fertile Crescent. It moved them back earlier in history, thanks to the information provided in these trees. This is a cool adaptation to fire. This particular pine has two kinds of cones on it. It has open cones that are going to make seeds available to dispersal agents like Clark's nutcracker, and that are going to be able to fall out of the cone when it hits the ground. And then it has closed cones like this one, a serotinous cone, and it's sealed up and will only be opened by fire. It's setting itself up to be able to reproduce in a normal year, but also to take advantage of the conditions created by a fire when there's a pulse of nutrients to the soil and an exposed mineral seed bed that might be an especially good opportunity for this tree to reproduce out of these cones that will open right when that fire comes through. The White Mountains are made up of many different kinds of sedimentary rock, which is rock that was formed on ancient seafloor. And so initially, it's sand, mud, and the skeletons of marine animals. So at the coast in California, you can see unmetamorphosed sandstone and mudstone. Here in the mountains, this is red quartzite. This is metamorphosed sandstone. And the way that that happens is that that sandstone, that ancient seabed, as it was lifted and folded by tectonic processes into what's now the White Mountains, it was also heated. And as it heated, some of the glass in the sand melted, and so some of that sand fused, and the rock became harder and denser as a result. And what we're sitting in here is a talus field. So the reason that there are a whole bunch of smaller rocks around me rather than a big continuous block has to do with water getting into cracks in the rock in the summer or when it's above freezing temperatures, and then freezing into ice during the cold time of day at night. That ice expands, it pushes apart the cracks, and you can see that even small cracks like this over time can expand to the point where the rock breaks up into pieces. The bristlecone don't grow on dolomite because they like that environment particularly, but they're really stress-tolerant individuals, and so that species is able to persist on the dolomite where other plants aren't. If you look to my left, you can see bristlecone pines and relatively few things in the understory. And that's on this white dolomite soil surface. If you look a little bit behind me and to the right, on the other side of this drainage, you see the red quartzite substrate and a lot more shrubby vegetation. That shrubby vegetation makes it more difficult for a bristlecone pine seedling to successfully reach mineral soil, establish, and then acquire the nutrients, water, and light that it needs to survive. And so for that reason, more than any special advantage that the dolomite soils provide, bristlecones are not able to establish in the red quartzite as well. Another feature that's interesting is that in this harsh desert environment, even though cold is the predominant experience up here, the temperature can get really, really high in the summer, and that high temperature can cause a lot of water stress for plants here. So the white surface is reflective, and it just keeps the ground temperature a little bit cooler, reducing evaporative water losses compared to a darker substrate. I'm now at 11,400 feet, or about 3,500 meters, in the Patriarch Grove of the bristlecone pine forest in the White Mountains. One of the interesting things about bristlecone pine is that even at this elevation, it grows relatively upright and straight. In other places in California and with other tree species, we see certain growth forms characteristic of the subalpine zone and reflective of what it's like to be a tree in such extreme conditions. So there are flag trees, trees from which all of the branches have been killed by desiccating winds on one side so that there are only branches coming off of the other side of the tree, the lee side of the tree. And then there's a more extreme growth form called Krummholz trees. And Krummholz are formed when growth is really only possible if the tree is sheltered by the snowpack or in the lee of a rock. And so growth is forced to hug the ground or to conform to the contours that the wind follows as it blows over a rock from the windward to the leeward side. And in order for a tree to form Krummholz, it has to tolerate and be able to grow at meristems, at growth regions other than the apical meristem that's at the tip of a typical conifer. So one of the adaptations of some of the tree species like whitebark pine and limber pine to the subalpine environment is to be able to grow at other places than that apical meristem at the tip, to be able to grow out to the side from other branch points. Another thing about the subalpine that is characteristic of all of California is that it has really low vertebrate diversity. And it's similar to the alpine in that the major species you find here are all adapted to these broken rock and talus environments. So some of the characteristic animals of the subalpine zone are the American pika, the yellow-bellied marmot, alpine chipmunk, Belding's ground squirrel, and then certain birds. One remarkable bird of the subalpine is the Clark's nutcracker. And Clark's nutcracker have a remarkable ability to scatter hoard. So they collect seeds from limber and whitebark pine that are relatively large pine seeds adapted for this purpose, and they hide them, and they can hide up to 98,000, so on the order of 100,000 individual seeds in different places on the landscape, and then find them later, and they have an uncanny ability to find them even when the ground's covered with a meter of snow. The nutcracker itself is a really interesting species adapted to scatter hoard in that extreme way and in that way to survive in this environment. But the other role that it plays is that it disperses the seeds of those tree species, and so they've evolved larger seeds to be attractive to the birds. The sun's setting and the temperature's dropping, so we're going to leave the bristlecone pine forest with a view of the Great Basin and the rest of the ranges that support this incredible subalpine species.